Good morning, everyone. I'm Engineer Lakshana Patirage, and it's my pleasure to welcome y'all to the insightful webinar on green hydrogen energy from concept to implementation. Thank you for joining with us today. We have a highly esteemed speaker with us who will share his expertise on this crucial topic, and we are excited to have an engaging discussion. Before we proceed, I would like to invite Dr. Konara to introduce our distinguished speaker. But first, let me briefly introduce Dr. Konara. Dr. Engineer KMSY Konara is a senior lecturer attached to the Department of Electrical and Information Engineering, Faculty of Engineering, University of Ruhuna. Dr. Konara graduated from University of Ruhuna in 2013 and completed the MSc degree in renewable energy at University of Agder, UIA, Norway in 2016. His master's thesis was awarded as the best master's thesis in renewable energy at UIA in 2016. Dr. Kunara earned his PhD degree in renewable energy from the same university, Norway, in 2023. His PhD research was on the enhancement of charging resource utilization of a fast charging station with the help of renewable energy resources. He has involved and contributed for several renewable energy industrial projects carried out and supported by Agder Energy Net AS, Teknova AS, Eltec AS, Norway, the Energy and Resources Institute, TERI, India, and Research Council of Norway, etc. His research interests are renewable energy systems, charging coordination of electrical vehicles, and smart grids. His peer-reviewed research publications across over 30 in international index journals and conference proceedings, and some of his research works presented at the conferences have been awarded as the best papers. He has been an active member of the organizing committee, advisory committee, program committee of various international conferences, including IEEE and Springer conferences. Dr. Konara is an awardee of the President's Award for Scientific Publications in 2020 as well. So, over to you, sir.
Thank you, Engineer Lakshani, for your generous introduction. Actually, even though it was not expected, you have given me a very generous introduction. Thank you very much for that one. Actually, uh, uh, my duty and responsibility in this forum today is just to introduce our speaker, Professor Mohan Lal Kohli. I consider it as a great honor and privilege to introduce Professor Mohan Lal Kohli to the audience. So first of all, I must extend my sincere thanks and the gratitude to Professor Mohan Lal Kohli for accepting our invitation to be the speaker for today's event. So let me to introduce our speaker to the audience. Professor Dr. Mohan Lal Kohli is a full professor in smart grid and renewable energy at the Faculty of Engineering and Science of the University of Agder, Norway. He is a leading renewable energy technologist with 3 decades of academic experience at the international level. He has previously held academic positions at the world's prestigious universities like University College London, UK and Australia, University of Dundee, UK, University of Jyväskylä, Finland, Hydrogen Research Institute, Canada, etc. In addition, Professor Mohan Kohli was a member of the Government of South Australia's first Renewable Energy Board from 2009 to 2011 and worked on developing renewable energy policies. Professor Kohli is an expert evaluator of many prestigious international research councils, such as European Commission, Erasmus Plus Higher Education, International Capacity Building Program, Royal Society London, UK, Engineering and Physical Sciences Research Council, UK, Cyprus Research Foundation, etc. In addition, many international organizations have invited him to deliver keynote addresses, expert lectures, workshops, etc. He has also been a member of many academic promotional committees as well. Professor Kohli has been successful in obtaining competitive research fundings from prestigious research bodies such as Norwegian Research Council, European Union, EPSRC, BBSRC, NRP, etc., for his work on sustainable energy systems. His work on energy systems and electrical and electronic engineering has been recognized in the top 2% of scientists worldwide consistently from 2022 to 2023, according to the Stanford University matrices based on Elsevier data. His top 10 publications have received an average of more than 200 citations each, making him an acknowledged pioneer in his profession on a global scale. Dear ladies and gentlemen, today we have invited such a prominent academic from University of Agder. Again, thank you for accepting our invitation, sir. And please, I kindly invite for you to deliver your talk to the audience. Over to you, sir.
Thank you very much, Dr. Konara. I'm very grateful to Institution of Engineers Sri Lanka and especially Electrical and Electronic Telecommunication Engineering Wing for organizing this webinar. I'm very delighted to be with you and to share some of my experience of working on green hydrogen energy technology. Dr. Kunara is associated with me as a student, master student, PhD student, and then of course academic collaborator from last 1 decade or even more than that. And I'm actively working in collaboration with Konara for doing research work, joint teaching related to sustainable energy technologies. Dr. Konara has requested me through Institution of Engineers Sri Lanka to share my 3 decades of experience of working on green hydrogen energy technologies. I will share my screen now. Konara, can you enable to share my screen? Hello, Konara. Hello, Jahira. Can you allow me to share my screen?
Yes, yes. Can please just check, sir?
Yes. Not it. Or you can make me co-host maybe?
Oh, yeah, sure. Please check, sir.
Yes, now it's okay. Good. Is it coming now in the full screen mode?
Yeah.
Very good. So thank you, Konara. So coming back to my background and having association with Sri Lanka, few years before, University of Agadar is having very active cooperation with Ruhuna, University of Ruhuna. And that cooperation helped us in bringing Sri Lankan students here in Norway for doing masters in renewable energy. And Kunara also participated through this program for doing his master thesis with me. So University of Agadar is having very active cooperation with Sri Lanka, and we want to enhance that academic cooperation using Institution of Engineers Sri Lanka, as well as developing some joint research projects also. So today, the topic is green hydrogen from concept to implementation. This is a very interesting topic. As all of us, we know that most of the countries in the world, they are trying to move towards the renewable energy system. Many countries, they have signed the agreement by 2030 they want to contribute significantly. I don't remember the percentage, but by using renewable energy. Considering all this background into account, Sri Lankan government has also prepared hydrogen energy policy. As per hydrogen energy policy of the Sri Lanka, it is expected that by 2030, in this green hydrogen energy sector, around 4,000 jobs will be created. And when we are preparing this green hydrogen, then of course there is going to be foreign investment in Sri Lanka of around 10 billion US dollar. And it is also expected, as per the policy document, that 1 billion investment for domestic production and utilization of green hydrogen and associated technology. Sri Lanka has a big scope for offshore wind farm. As per the policy document, it says that by 2030, around 4 gigawatt offshore wind farms will be installed, and most of them will be used for producing the green hydrogen. So to produce the green hydrogen by using offshore wind farm or onshore renewable energy, we will need infrastructure. To get that infrastructure, of course, we will need some skilled professionals, investment, and to make it operating. So we can see that the green hydrogen energy from concept to implementation, how we can get it done. So this is a very interesting point. Now, we are talking about green hydrogen. It means that most of the hydrogen should come from renewable energy sources. As we have seen that when we are talking about the green hydrogen and especially using the renewable energy sources, for example, wind farm, then we have to use electrolysis process for getting this hydrogen. Hydrogen is a very good energy carrier due to its high mass energy density. Hydrogen is required in many applications, process industries, making fertilizers, steel industries, so on and so forth. So at this moment, around 95% of hydrogen is coming through natural gas reforming or from the hydrocarbons. And all of us, we know that due to the economic situation and other factors, it was very expensive to import the hydrocarbons in Sri Lanka also. So I feel that considering those factors into account and the availability of offshore wind farm within Sri Lanka of around 40 gigawatt, and it is expected that by 2030 it will be around 4 gigawatt. So that offshore wind farm or the renewable energy can be used for producing the hydrogen, and that hydrogen can be a good energy carrier and can be used in place of hydrocarbon gas for different applications also. In recent geopolitical situation, we observed that Sri Lanka was in need of fertilizers, right? Of course, then hydrocarbon is required. And due to the economic situation and geopolitical situation, it was very expensive. So this hydrogen, which we can produce locally, right, using our available offshore wind farm, then that hydrogen can be used in making the ammonia and the fertilizers which we required for our sustainable agriculture production also. Considering all these factors into account, I believe that Sri Lanka has a good potential to move towards the hydrogen based economy by producing the locally green hydrogen. Now, coming to this slide, it says that by 2050, if we want to replace our fossil fuel based economy with hydrogen oriented economy, then this most of the hydrogen has to come from renewable energy sources. It means that we are trying to do decarbonized society, right, using hydrogen. So hydrogen production and then of course distribution and utilization is going to be very important when we are talking about hydrogen economy or to replace our hydrocarbon economy by using locally produced hydrogen. So for that, we need to move by using many steps, through many steps. So how we are going to produce the hydrogen? Okay, how we are going to store that, how we are going to distribute that. And then of course, when we are going to have the hydrogen, we need appropriate plan for hydrogen utilization, whether we are going to use hydrogen as a fuel in fuel cell engines or internal combustion engine or in the process industries, as well as making the ammonia and to use that ammonia for the fertilizer also for making our sustainable agriculture production. So here the final aim is that we should have the hydrogen from renewable energy sources. Okay, so how we can get that one, that we will study or that we will learn through this lecture by using my 3 decades of experience of working on green hydrogen energy technology, how those concepts or those technologies can be implemented within the Sri Lankan context. Okay, so now we are talking about hydrogen economy. We know that at this moment, around 95% hydrogen is coming through hydrocarbon reforming. Again, for the hydrocarbon reforming, there is going to be carbon footprint, and of course, we have to import the hydrocarbon gases also. But our objective is to produce the hydrogen locally by using renewable energy sources. And as per the policy document of Sri Lanka, it says that around 40 gigawatt offshore wind farm can be installed across the Sri Lanka. It means that the wind is having very good potential, right? And of course, we can consider the solar photovoltaic also, and in some cases, hydropower also. So when we have these renewable energy sources, so these renewable energy sources, intermittent electricity can be used for producing the electrolytic hydrogen. In some cases, if we have the nuclear power plant, we can use the nuclear electricity also for producing the hydrogen. When we have the nuclear power plant, like in some cases it may be possible, right, depending on the country also. So that heat can also be used for this hydrocarbon reforming also. When we are getting the hydrogen, like especially with focus on green hydrogen, it means that through the electrolytic process in which we are utilizing the renewable energy, so that electrolytic hydrogen is basically energy carrier with high purity. So that pure hydrogen can be used in many different applications. It can be used in internal combustion engines also. It can be used as a fuel into the fuel cells also. And of course, within the industry, we need hydrogen, for example, in steel industries also, and of course, in fertilizer industries also. So all process industries, we will need the hydrogen. So here, this hydrogen is going to play a major role in replacing the hydrocarbon and replacing the import burden of hydrocarbons on the government's economy or our economy, right? So to get that hydrogen, we can use locally renewable energy sources. And this hydrogen through electrolytic process is very pure, okay? So that can be used in the fuel cells also. Fuel cell is a very good device in which we can use this pure hydrogen, and it is a stationary device, electrochemical device. Depending on its capacity and operating temperature and the type also, we can use it in different application, for example, transport, building, and industry applications also. So here, when we are talking about the green hydrogen, okay, that is the main focus, right? So that green hydrogen, by we can use in heavy duty vehicles also. In heavy duty vehicles, where we have the internal combustion engine, with slight modification, we can use hydrogen as a fuel. And of course, we are trying to produce this hydrogen locally using renewable energy sources. It means that we are going to reduce our import burden. Then when we have the hydrogen as a pure fuel, right? So then in the fuel cells, okay, that is another very good option. And of course, for the process industries also. But now here you can see that IC engine is well established technology. Process industries, they are also well established. But for the fuel cells, okay, it is still upcoming technology. So let's say if we focus on the fuel cell, then we can have some classification of the fuel cell. In different type of fuel cells, we can use different type of fuel. For example, when we have the pure hydrogen, which we are going to get through this electrolytic process using renewable energy sources, then we can use that hydrogen in proton exchange membrane fuel cell and alkaline fuel cell also. This hydrogen can also be used in making methanol, ethanol, and that can be used in direct methanol fuel cell also. So these direct methanol fuel cells, they are very good for small or portable power application. And if still we have some hydrocarbon facilities available, within that hydrocarbon, we can inject this hydrogen further for making it hydrogen, or maybe having more hydrogen percentage compared to the carbon. That can be used in molten carbonate fuel cell or solid oxide fuel cell. This molten carbonate fuel cell and solid oxide fuel cell, their operating temperature very high. So they can also be used for combined heat and power applications where we need the heat for some process industries also. And of course, when we are having the temperature and by using some reforming process, we can get the pure hydrogen and we can use into the proton exchange membrane fuel cell or phosphoric acid fuel cell also. So depending on the type of the fuel, depending on the capacity also, these fuel cells can have different applications. Portable application, transport application, stationary applications. So here we may focus on the transport and the stationary application. In the transport, depending on the capacity, we can use the fuel cell for the road, maritime, aviation sector also. Stationary, we can use for the residential application as well as the industry applications, right? So here you can see that when we are going to get the green hydrogen using renewable energy sources, and we can use them in different sector, and maybe if we focus on the fuel cell sector or utilization of hydrogen within the fuel cell, then you can see that what different type of fuel cells are available and how we can utilize them in different applications also. Now, we are talking about hydrogen production. Of course, we are talking about hydrogen utilization as a fuel into the fuel cell. To use that hydrogen which has been produced through the electrolytic process, right? We have to consider that how we are going to store it, because storage is again a big challenge. Whether we are storing that hydrogen into the compressed form, cryogenic form, metal hydride form, and then we have to see that how that hydrogen is going to be delivered at the application point also. If we take the Sri Lankan case, and if we are going to use the offshore wind farm for producing the hydrogen, then naturally that huge amount of hydrogen can be exported through the port, okay? And then basically it comes under the delivery, and then storage, mainly it will be in the compressed form also, okay? So here you can see that how we have to consider different approaches, okay, for taking into account the hydrogen economy. So when we are going to integrate all these things together, we need to do the technology validation also. So every system here is working on different characteristics. Okay, they may have different operational characteristics. Due to that, it is challenging how we are going to do the system integration also. When we are talking about the system integration, at the same time, we have to consider about hydrogen safety also. As we know that hydrogen is highly flammable, so we have to consider from the safety point of view, right? Whatever the system we are using, we have to see that hydrogen should not get leaked there. And for that, how we have to consider the safety issues also. And when we are talking about all these things together into account, so for that, we will need some codes and standards. Then only we can move towards the hydrogen economy, right? So now here you got the idea that when we are talking about the green hydrogen and green hydrogen economy, so here you can see that how we have to work on different aspects, and so that in an integrated manner we can move towards the hydrogen economy. So now I have just given you the very high level overview to create your interest on the green hydrogen energy system. So now I will share with you some of my working experience on hydrogen energy projects. Long back in 2006 and 7, I was working as a research director at University of Jyväskylä, Finland. And with the help of European Union funding and of course industry funding, we developed solar hydrogen energy system. So this solar hydrogen energy system within the university, it was developed, let's say 20 years earlier. Okay, so how that system it was? So here the system was that when we have the excess energy available from the primary renewable energy sources, for example, wind turbine or the solar photovoltaic system, how we can use that energy for producing the green hydrogen. In this project, right, there was some industry partners also. So those industries, they were from the central Finland. and mainly the power industries, they had to run their power plant or combined heat and power plant during the winter time for providing the heat to the district, but they were having the excess electricity also. So that excess electricity, in addition to renewables, can also be used for converting that through the electrolysis process for producing the hydrogen or storing the energy in the form of hydrogen. So this project, it was a solar hydrogen energy system project at University of EESL of Finland. So here you can see that when we are providing that excess electrical energy through some power conditioning devices to the electrolyzer, we are producing the green hydrogen and of course the oxygen as a byproduct also. And then after doing the purification and everything, that hydrogen can be used as a fuel into the proton exchange membrane fuel cell. And when we are using that hydrogen as a fuel in the PAM fuel cell, so of course we need to have some loading also. So here in this case, we consider not only first electric load, of course, but in addition to that, a hydrogen fueled car also. So here you can see that in this diagram, this is a single passenger car, hydrogen fuel using proton exchange membrane fuel cell. Okay, and we tested this car in the Nordic climatic conditions. And the students, they were able to do the project on electrolyzer characterization modeling and analysis, fuel cell characterization modeling and analysis, and of course on many aspects of this project also. So you can see that 20 years before when I started working on this project, so the learning from this project is going to be very useful when we want to have the implementation of the hydrogen energy system. And what we have seen from the Sri Lankan government point of view, that by 2030 they want to utilize 4 gigawatt wind farm for producing the green hydrogen. So here you can see that the concept what have worked in early 2000 can be implemented, right, in such type of project where we are trying to integrate wind turbines for producing the green hydrogen. Okay, now moving forward, then when I was working at University of Dundee, Scotland, there I had another project. That project, it was related to proton exchange membrane fuel cell stack modeling for dynamic loading. So earlier, I mentioned that proton exchange membrane fuel cell can be used for the transport sector also. And within the transport sector, we know that we are going to have very dynamic loading. So under that condition, how the proton exchange membrane fuel cell is going to work, that had been considered when I was working at University of Dundee, Scotland, and that project was in cooperation with Robert Gordon University, Aberdeen. Also, it was in 2007. Then, long back, maybe early 2000, when I was working in Canada at Hydrogen Research Institute, so I developed one proposal in which we tried that if we are going to use the fuel cell for power system stability and improvement, so how we have to develop appropriate control algorithm, and how that hydrogen fueled fuel cell can help us in to manage the peak power demand and system stability. And for that, how we need to develop appropriate switching sequences for power conditioning devices for managing active and reactive power delivery, that have been considered, you see, in 2003. So I feel very happy that work which I did long back, now it is going to be useful for this hydrogen energy implementation. Now we will come to the focused work on how we have to integrate renewable energy sources for storing the energy in the form of electrolytic hydrogen, and how we have to utilize it considering the decentralized power generation point of view. Okay, so this is a very interesting topic considering today's focus on green hydrogen energy technology. It means that when we have intermittent renewable energy sources, we need appropriate energy storage to overcome the intermittency of these renewable energy sources. So in this case, we can use hydrogen as an energy carrier, or in a simple way, electrolytic hydrogen as a long-term energy storage, okay, to overcome the intermittency of renewable energy sources and making the system more decentralized. So considering this factor into account, now I'm sharing with you some of my experience of working on this project. So in this project, standalone wind and photovoltaic have been used as primary renewable energy sources with objective that to store the excess energy from the primary renewable energy sources, wind and photovoltaic, in the form of electrolytic hydrogen. It means that we are producing the green hydrogen utilizing the renewable energy sources. And then when we have this stored energy in the form of electrolytic hydrogen, we need to reutilize for supplying the required amount of energy also. That's why I mentioned the decentralized system. So here, when we are talking about utilization of renewable energy sources for hydrogen production, so we need to work on how we have to consider electrolytic hydrogen production system and of course storing of the hydrogen also. Then there should be one additional point here, because we are talking about standalone decentralized system, then we have to reutilize that stored energy in the form of electrolytic hydrogen, okay, for what purpose? For producing the required amount of electrical energy. So then hydrogen utilization and subsystem should be there, okay. So sorry, then of course when we have all these systems together, right, we need to have some control system. And when we are operating such type of system, we have to do some operation and performance analysis and the conclusion that I'm going to provide you. So now our focus is that we want to store the energy from the renewable energy sources or convert that renewable energy into the electrolytic hydrogen. And of course, then we need to reutilize also. So in this project, the focus was that reutilization through the fuel cell, which is relatively more complex compared to conventional battery storage system. In the market, most of the technologies, they are available, okay, but to integrate them in a standalone applications, right, it is a challenging also. So how we have to see that how we can integrate them. And after integration of this different renewable energy technologies together with aim of hydrogen production and utilization. So for that, of course, we will need some appropriate control strategy and power conditioning devices also. And those have been developed and successfully tested in this project also. Now here, with the help of this single line diagram, you will be in a position to understand how this green hydrogen energy system can work, where we are trying to integrate renewable energy sources. If we take the Sri Lankan case, in Sri Lankan case, the main focus is on offshore wind farm. And of course, it also says that some solar photovoltaic can also be integrated there. So let's try to understand this project and how the learning from these projects can be further enhanced or expanded for the bigger project or for the implementation point of view. Let's say here we have the primary renewable energy sources, wind turbine and the solar photovoltaic system. So these primary renewable energy sources, they are going to produce the intermittent electrical energy. And here, what I mentioned that we are trying to have decentralized approach. It means we should have some decentralized load also and the standalone application also. So I will explain with the standalone application point of view. Let's say with reference to the load, if we have the excess energy available from this primary renewable energy sources, that excess energy has to be converted from the long-term energy storage point of view in the form of electrolytic hydrogen. It means that we need to have electrolyzer into account. Okay, we are talking about storing the excess energy in the form of electrolytic hydrogen. Then, of course, whenever we don't have the appropriate energy available from the primary renewable energy sources, then we need to reutilize that through the fuel cell for producing the required amount of electrical energy, right? So it means that we have to take into account the fuel cell also. So now let's come one by one. We know that wind turbine is intermittent, okay, depending on which type of electrical generator we are using here. Okay, similarly, solar photovoltaic intermittent DC power output. Okay, and we are talking about the electrolyzer, we are talking about the fuel cell also. Electrolyzer, electrochemical device, it needs DC power supply. We need to do the complete operation in an autonomous manner, so we need some reference level also. And here you can see that every system components, they are having very different operational characteristics. Considering all these factors into account, here the DC bus have been used, and this DC bus is taken as a reference bus. It means that the architecture which have been used for integrating these renewable energy sources and storing the excess energy in the form of electrolytic hydrogen using DC microgrid approach. Okay, so here you can have an additional learning also how we have to integrate different renewable energy sources together to on using on DC bus or maybe using DC microgrid approach. So this DC microgrid approach can have additional benefit also if we are going to have electric vehicles also. So this DC bus can also be used for charging of the electric vehicles also. Okay, and Kunara did PhD on the electric vehicle charging also. So that work can also be integrated here. So now focusing on green hydrogen here, let's say when we have the excess energy from these primary renewable energy sources with reference to the load and considering the energy level at the DC bus and using DC microgrid approach, we need to transfer that excess energy to the electrolyzer for producing the electrolytic hydrogen. Okay, so now here we are talking about the DC bus, we are talking about the electrolyzer. So electrolyzer, electrochemical device needs DC voltage or DC power supply, but it may have the different rating. This DC bus may have the different rating. So we need DC-DC converter or power conditioning device here to integrate that electrolyzer on the DC bus. Similarly, in this case, this wind turbine, it was a permanent magnet synchronous generator. It means that it was producing variable voltage, variable frequency output, which we cannot supply directly to the DC bus. So of course, for that, we need to have some regulator or power conditioning devices. Okay, that's very important here. Similarly, photovoltaic array, we know that we have to operate them at the maximum power point tracking. So we need to have some PV array and regulator here, and we can integrate them on the DC bus. And of course, we have the load, and there should be some energy level at the DC bus for maintaining the sustainability of the voltage on this DC bus also. So here you can see that wind turbine is having very different operational characteristics. Photovoltaic is having very different operational characteristics. And of course, we have the load dynamic also. And then considering this factor into account to make some reference, this energy level at the DC bus is going to be very important for doing the operation. So let's say when we have the excess energy from these primary renewable energy sources with reference to the load, and then when we want to transfer that energy to the electrolyzer for what purpose? To store that in the form of electrolytic hydrogen. Then of course we need to have some controller here. So let's say here we have the master controller. So this master controller makes the decision based on the energy level are based on the energy availability from the primary renewable energy sources with reference to the load, with reference to the energy level at the DC bus, and then sends the information to the microcontroller or the subcontroller, which is basically controlling the operation of the electrolyzer here. So then this microcontroller can help in doing the power switching of this DC-DC converter for transferring that excess energy with reference to the energy level at the DC bus to the electrolyzer. Okay, so you see how we are integrating, renewable energy sources, knowledge of electrical engineering also in this electrochemical device. It means that we need to have more integrated approach of multidiscipline engineering together. Okay, so now let's say that excess energy which have been provided to the electrolyzer, right? So then electrolyzer is going to produce the electrolytic hydrogen, right? So due to this electrolysis process, that hydrogen is going to be very pure, right? So this electrolyzer, it was at the normal atmospheric pressure, but nowadays we have some electrolyzer, they are available at relatively higher pressure also. So of course we are focusing on storing the hydrogen into the compressed form. So you can see here the hydrogen which have been produced by this electrolyzer. So initially it was at the atmospheric pressure, then it has been compressed at a particular pressure and stored into this storage tank. Right? So here you see how we are storing the excess energy from the renewable energy sources in electrolytic hydrogen form. So here, if we consider only from the hydrogen production point of view or green hydrogen production point of view, so you can see that how these power conditioning devices which have been developed under this project, how this controller which have been developed in this project, right, how they can be implemented into the field for storing that excess energy in the form of green hydrogen. So you see, our title of our today's topic is like green hydrogen from concept to implementation. Now we are at the implementation phase. And as per, if we consider the Sri Lankan situation, it says that by 2030, around 4 gigawatt offshore wind farm will be installed, and those will be used for green hydrogen production. So some of the learning from these projects will also be useful for this planned project of green hydrogen. Okay, so the results from this project and all details, they have been widely published in leading journals, including International Energy Agency also. So if you are interested, you can refer them. So now coming back to this project, this is a decentralized project and we are talking about the excess energy also, but at some point we may have the deficit of the energy also. Let's say when we have the deficit of energy from the renewable energy sources with reference to the load, as well as taking into account the energy level at the DC bus, then of course the energy which we have stored into the form of electrolytic hydrogen has to be utilized for the within the fuel cell as a fuel for producing the required amount of electrical energy. So in that case, then this master controller, based on this information of the primary renewable energy sources, load, energy level at the DC bus, can take the decision and send that information to microcontroller for starting the operation and utilize this hydrogen which we have stored, in which we have stored the energy as a fuel for producing the required amount of energy. So we know again, this fuel cell is electrochemical device. It is going to produce the DC output. So we cannot directly connect at the DC bus. So to transferring that excess energy, we will need here boost or DC-DC converter also. And of course, as per the fuel, as per the output requirement, we have to control the fuel injection into the fuel cell also. Then is what I was mentioning earlier, that we can use hydrogen as a fuel in internal combustion engine also. So if suppose we don't want to use this fuel cell, but we want to use the internal combustion engine, then also we can use this stored hydrogen into this internal combustion engine, and then this internal combustion engine can be coupled to the generator and we can produce the electricity. And of course here we are talking about making a reference level, so we will need the rectifier and so on. I believe that with the help of this single line diagram of the project, you will be in a position to understand that how we have to integrate renewable energy sources with different characteristics, okay, by using power conditioning devices and for storing that excess energy from the renewable energy sources in the form of electrolytic hydrogen, and then how we have to utilize that stored energy in the form of electrolytic hydrogen within the fuel cell or internal combustion engine for producing the required amount of electrical power. So now here in the single line diagram, you can see that how these different power conditioning devices and the controllers, they have been integrated together. Okay, so we know that when we are supplying that excess energy to the electrolyzer with reference to the DC bus, with reference to the energy level at the DC bus, right? So that electrolyzer, of course, we have main focus on hydrogen. Okay, so that hydrogen is stored and we used as a fuel into the fuel cell system. But this electrolyzer is again producing the oxygen as a byproduct also. When we are operating the fuel cell, we need oxidant also. So in the first stage of the project, compressed air have been utilized as the oxidant. But if we have this oxygen here, right, which is a byproduct from the electrolyzer, if you purify it and store it, then we can utilize it in place of compressed air into the fuel cell system for producing the electrical energy, and then naturally the operational efficiency of the fuel cell is going to be increased. So here you can see that, right, how we can do further modification with reference to this project also. So this oxygen which has been produced here as a byproduct here, right? So that oxygen is also very poor, and we have seen during our COVID period or that how oxygen it was important for our survival also. So this oxygen can also be used for medical purpose also. Okay, so there is a lot of things which we can integrate together in this green hydrogen energy project. So here I was talking about the DC bus, and on the DC bus we have to maintain the energy level. It means that we need to include short-term energy storage on the DC bus for maintaining the voltage sustainability also, and for calculating the energy level at the DC bus, for deciding the operation of electrolyzer and the fuel cell so that we can avoid simultaneous operation also. So those all factors or parameters are monitored by master controller for taking the decision and accordingly then sending the information to electrolyzer controller as well as fuel cell controller. Now if we move towards more uh, complex or more complete single line diagram of this project, right? Here you can see that what we were talking earlier, that from electrolyzer we have the oxygen as a byproduct, so that oxygen can be stored here and used as a fuel into the as a oxidant into the fuel cell for producing the required amount of electrical energy, right? So here I will just give you some specification of the system components. So this was a very small system, and this small system, in this small system wind turbine, it was of only 10 kilowatt capacity, but now we are talking about the gigawatt capacity. You see now the scale, okay? So that you can see the concept to implementation. Now we are moving from that point. Here it was very small capacity of 1 kilowatt, and the target load it was of the 5 kilowatt. Considering the target load capacity of 5 kilowatt, the electrolyzer it was of the 5 kilowatt capacity, fuel cell also it was of the 5 kilowatt capacity. Electrolyzer it was alkaline type, fuel cell it was proton exchange membrane type. Okay, hydrogen stored into the compressed form of 10 bar, oxygen also purified and stored, and at a particular pressure of 8 bar, okay, and then that have been supplied to the fuel cell. when when this master controller takes the decision based on the energy level at the DC bus, based on the energy available from the renewable energy sources with reference to the load, and so on and so forth, right? So here, to make the system more as a test bench, programmable power source and programmable load, they have been used also. So if we move forward, these are the specification of this system. We will not go in much detail because I know that we don't have that much time also. Few minutes are left. So here you can see that this is the electrolyzer of 5 kilowatt, power fuel cell of Ballard power system 5 kilowatt, big cable it was for the wind turbine, small cable it was for the photovoltaic. Okay, the computer it worked as a controller for the electrolyzer. This computer it worked as a controller for the fuel cell, and this computer it was for the main controller here. And behind the wall, then there was a short-term energy storage battery bank for maintaining the voltage level at the DC bus. And already you have seen that hydrogen it was stored outside also at a compressed form also. And then this cylinder, it was compressed air which we used as the oxidant into the fuel cell. So this is a very interesting project, okay, and I believe that the learning from this project will be very useful for implementing this green hydrogen energy system. And these were the power conditioning devices, DC-DC converters, which have been used for connecting the DC bus, okay, electrolyzer, and from fuel cell to DC bus. Okay, so and all of us we know that they are very operating at very high efficiency also. Some of the results I have shown here for a single day, how the photovoltaic power was there, wind power was there, and with reference to that, how the hydrogen production, consumption, utilization was there, how the load were varying. And here you might have observed that the controller have taken care that both fuel cell and electrolyzer they should not operate simultaneously also. And you might have seen there are some transients right in the electrolyzer input power. Okay, so what that those transient it was due to the regular starting of the compression. Because if you remember earlier I was mentioning that this alkaline electrolyzer which have been used in this project was at atmospheric pressure, and when that atmospheric pressure buffer storage tank is full, then it has to be compressed and stored in a particular pressure. So that has going to be in a cycle, right? So then compression energy also has to come from the DC bus. That's why here we have the transients of the supply of electrolyzer input power, right, in a cyclic manner. Okay, and then of course here this hydrogen production it is not looking like a continuously, because the hydrogen flow meter it was installed after the compression. That doesn't mean that electrolyzer was not producing the hydrogen continuously. Okay, only the measurement device it was kept after the compression, right? So you can observe here, right, how the intermittency were there with reference to the power, and then how we are producing the hydrogen and like that. So it's very going to be a very complex system also. Then of course in this slide you can see that how the current at different buses they were varying, and how the utilization factor, energy efficiency of the electrolyzer, fuel cell they have been calculated also. And as I mentioned that DC source have been used for creating this different type of patterns of renewable energy sources for testing the system and the control algorithm for different input energy conditions. And in the second point, the energy level at the DC bus have been mentioned for starting the operation of electrolyzer and fuel cell, and to avoid the overlapping of them also, right? So and then again this point is very important, how the short-term energy storage helps in deciding the energy level at the DC bus, and how it can help us in storing that excess energy from the long-term point of view in the electrolytic hydrogen point of view. On this typical day of operation, you can see that how much energy have been used for converting the hydrogen, how much utilization factor was there, and energy efficiency also, right? So and then same on that typical day, fuel cell also started. So how much hydrogen have been used into the fuel cell for producing the electric required amount of electrical energy, and then of course utilization factor and energy efficiency also. So with the help of DC load and programmable source, right, the system can be tested for different input and output condition. Now here you can see that in this slide, the continuous operation of 28 days. So we don't have left time, but I will just go very briefly. So during this 28 days of 28 days of operation, you can see that how the electrolyzer input power was there, how the fuel cell power was there, how the battery charging, discharging were there, how the loading conditions were there. Okay, and then accordingly on this 28 days of operation, how the electrolyzer input power was there, how the hydrogen production was there, and so on and so forth. Okay, so all these technical results and their technical operational characteristics, algorithms, and all details, they are widely available in my published articles in IEEE sciencestarry.com, including International Energy Agency. If you have free time and if you have more interest, you can refer them and read them. The conclusion is that if we want to move towards the green hydrogen energy system, right? So some of the developed control system and power conditioning devices can also be used. And unique feature of this system is having so many different components with different characteristics. So how they are connected through power conditioning devices on the DC bus, and how the developed control strategy help in having autonomous operation of this system. And power conditioning devices, again, it is very important for transferring the excess energy from DC bus to the electrolyzer, and also of course from the fuel cell to the DC bus, right? So that is again a very important point here. And then the energy level at the DC bus is important also for sending the signals for starting the operation of electrolyzer and the fuel cell. And of course, we have to consider the system safety, reliability, and performance record also. And those utilization factor, energy efficiency of these components, they're also very important, okay? But those efficiencies are mainly controlled by electrochemical reactions. And of course, we cannot go much above a certain value, right? But the big challenge is that how we have to integrate them. So considering this, the project which I did, let's say 25 years before. So this project's long-term operation and encouraging experimental results show that a reliable autonomous renewable energy system based on long-term energy storage as hydrogen can be realized. Okay, and we can move towards the green hydrogen energy system. And of course, the Sri Lanka is moving for that one. So I feel very happy, and I feel that some of the work which I did 25 years before will also be useful for this big projects or gigawatt level projects in implementation also. So you can see that how the concept which I worked 25 years before on green hydrogen, now with reference to some modification, of course, how they are going to be implemented into the field. Okay, so thank you. Hello, Konara.
Thank you very much, sir. Engineer Lakshani. Engineer Lakshani, are you there? Engineer Sahara.
Yes, I'm here.
The session is over. I think
There are some questions in the chat. I wonder whether Professor Mohan would love to take them up.
Yes, I can see that some of the participants, they have some queries, right? So I will address them. So
Okay.
such type of system is quite interesting, And of course, it needs a lot of initial capital investment also. If we consider from the Sri Lankan point of view and that policy document, it says that if we are going for the 4 gigawatt offshore wind and hydrogen, so around 10 billion foreign investment will be required for that one, and around 1 billion investment into domestic production and utilization of hydrogen. So we are talking about the huge amount of money also. Okay, but here if we consider from the long-term point of view and from the project economics point of view, so it may be economical because we are in place of hydrocarbon, we are using locally produced hydrogen also. And of course, here, as per this hydrogen policy document of Sri Lanka, it says that around 4,000 jobs will be created also. Okay, so there is a quite good scope for economic development and industrial development of Sri Lanka, and of course for producing hydrogen locally and utilizing that hydrogen maybe for the green ammonia production and for the fertilizer also. So regarding the cost, okay, so wind farm cost is relatively going down, but of course it needs a lot of investment also. Electrolyzer is a very proven technology, especially the alkaline. From last 100 years, we are using that one for producing the hydrogen. So it is not that expensive also. Only the big challenge is that to get integrated and then investment will be required for this, installing this huge amount of wind farms and of course the electrolysis process also. And I don't have the idea at this moment that how much cost will be there for production of hydrogen of 1 kg. But I believe that in the range of $5 to $10 it may be, right? So depending on the cost of system components, basically the offshore wind farm and the electrolyzer also. But then when it comes to the utilization of hydrogen, so utilization of hydrogen into the process industries, for example, making the green ammonia, that is a well-proven technology and it has been widely used all over the world. Okay, so that cost is there. But if we are going to use that hydrogen into the fuel cell, okay, then this fuel cell technology is not still mature, and we need to do more economic calculations, especially for the fuel cell, because it is a upcoming technology, not very well matured technology. And then I can see that there is one student or one participant was asking about the seawater use for the electrolytic hydrogen production. So when we are talking about such type of system, green hydrogen system, and where we have pure electricity, okay, so of course then we need to we want to have the pure hydrogen, right? And we are using the electricity, so pure water will be required. So for using the seawater would mean need to have different type of electrolysis process. So I'm not at this moment, I may not be in a position to explain you much more about the use of seawater for hydrogen production also, but at some other point after doing some literature review, I may be in a position to explain you. And one student here or one participant he asked about the safety of hydrogen. So that is a very important point. We need to have the system which is highly flame proof. And if we consider any room where we have hydrogen by volume 2% also, then it is highly flammable. So we have to take care of that. It means that all the system components should be selected appropriately so that there should not be any hydrogen leakage, as well as the flame proof electrical equipments also. So one student or one participant is asking about the process efficiency also. So efficiencies are limited here. We know that wind turbine efficiency is limited, solar efficiency is also limited. All of us are aware about that one. And when we talk about the electrolysis process, so that efficiency again it is limited due to this its electrochemical reaction. So we cannot go over that efficiency which have been defined by the Nernst equation and like that, right? So that is also that limitation is there. Similarly with the fuel cell also. So maybe around 60%, we can say 50 to 60% energy efficiency of electrolyzer. Similarly, 50% energy efficiency of the fuel cell also. And solar cell efficiency, we know that 10 to 15%. And wind turbine efficiency, we know that it is also quite low. Okay, but the input energy on this wind turbine and the solar cell is free, so we can consider from that point also. Okay, so and compared to this one, if we take the battery energy storage system, storage system, which is more economical also and having very higher efficiency also, but there we can store the energy from the short-term point of view and utilize them immediately. But now here we have seen that we need the hydrogen for many different applications also. For example, ammonia, process industries, so on and so forth, right? So now considering that point of view, we need to use, or we need to convert that electrical energy from the long-term point of view into the electrolytic hydrogen, and then we are reducing the impact of hydrocarbon gases also. So I hope that I have addressed most of the questions of the participants.
Yes, sir, you have addressed all questions. So I would like to ask, are there any questions left?
Yeah, excuse me, Brother Sahara.
Mm.
Yeah, I'm listening. Yeah, I just want to know the overall efficiency conversion with a lot of conversion stages. Overall efficiency, can you give some rough idea about from generation of say wind energy from windmill to final, so up to the hydrogen, say hydrogen production, overall
So
efficiency in,
yes, I can
yes.
give you that figure. So let's say solar cell efficiency is 15 to 20%. Okay.
Okay.
So then when we are going to get that DC electrical energy output, okay, that we are converting through the electrolysis for producing the green hydrogen. So if we take the electrolyzer efficiency, energy efficiency, then it is around, let's say, 60%.
Mhm.
So if we consider from solar cell to hydrogen production, so 60% into, let's say, 20%. So that energy efficiency.
Mhm.
But let's say if you forget about the supply side, okay, but if we consider only from the, let's say we have the energy available, it may be coming from the renewables or maybe other. So if we take that conversion efficiency for providing electricity in production of hydrogen, that we can say 50 to 60%. Then if you are using that hydrogen for producing the electricity back again, so we can take that efficiency maybe 50%. Okay, so from that hydrogen input to the hydrogen production to hydrogen utilization to produce the electrical energy, if we take that combined efficiency, then maybe it is 25 to 30%.
Right. Thank you. And also electrolyzer performance with this intermittency of electrical energy from say wind power. So what is the how I mean electrolyzer performance with this intermittency?
Yes. So if we are using the alkaline electrolyzer, then we need to have the constant power supply.
Mm-hmm.
Because alkaline power alkaline electrolysis operation depends on the constant power supply. So to get that constant power supply, we need to have short-term energy storage to overcome that intermittency from renewable energy sources. One point. Second point, if in place of alkaline electrolysis, if we use the proton exchange membrane electrolysis process, then we may not need that short-term energy storage for providing the constant power supply. But then proton exchange membrane electrolysis process is relatively more expensive than the alkaline process.
Mm-hmm.
So that is the drawback there, right? But now we have a lot of intermittent renewables and like that. So many leading electrolyzer manufacturer, they are moving towards the PAN electrolyzer also. But the relative cost is higher there.
Mm-hmm. Okay. One more last question. How is the readiness of Norway for this green hydrogen?
Yes, because many Norwegian companies, especially NEL, and they are leading manufacturer of alkaline, and I believe that they have signed some agreement with Sri Lankan government also to provide that electrolyzers for producing the green hydrogen. And in Norway, most of the electricity is coming from the hydropower, so they treat it as a green electricity, and they are utilizing that hydropower for producing hydrogen and of course storing it in the compressed form and transporting to different location in all over the world. And of course that hydrogen is traditionally have been provided for production of ammonia and for the fertilizer also. So considering their Norwegian background and their expertise, so Norway is at a well-established position, right, to take part into the green hydrogen.
Thank you very much.
Thank you.
Yes, sir. So, Engineer Tisa is actually the chairman of the Chemical and Process Manufacturing Engineering Sectional Committee. So,
Very
he's
good.
also very much into green hydrogen. In fact, he has initiated a discussion with some stakeholders this Thursday. So, we are a lot of interested in green hydrogen.
Very
And
good, very good.
today
So,
has
I mean,
been
I'm teaching this hydrogen energy course from last 25 years when I was at University of EESL, Finland, also in Dundee, Scotland, also, and recently also. Last year, I have given this hydrogen energy course for some international universities also. And then I believe that maybe in future we can have some international conference or symposium on green hydrogen in Sri Lanka also, because I'm chairing hydrogen energy, renewable energy and materials symposium from last 10 years, and this 10 successful years, right? In I mean, we have very good history, so I'm thinking maybe next year we may try to have that symposium in Sri Lanka also. And already I discussed with Konara, and he has shown his great interest on that one. And we may like to have some help from Institution of Engineers, maybe in hosting that conference within the Sri Lanka, maybe at University of Ruhuna or maybe at Colombo. Yeah, please.
Engineer
wonderful, sir.
Sahana,
Thank you.
I think Engineer Navodana has a question.
Yeah, go ahead. Yes. Did I miss it? I'm sorry.
Yes, thank you. Praveen, thank you very much for your marvelous talk. Actually, I'm one of former council member of IESL and a utility engineer. So I have very basic questions, some questions. First one, are there any commercial level hydrogen systems are using in the utility scale in the world?
Yes, because you see, from the hydrogen production point of view, okay, if we forget about the fuel cell, okay, so there are very megawatt capacity of hydrogen production facilities are there already. In Norway also, in United States, in Australia, many places, because we need hydrogen. And that hydrogen is used into many process industries, steel industries also, and main consumption in fertilizer industries also. So there are a lot of megawatt capacity hydrogen production plants using alkaline electrolysis process are in operation in around the world. But
Yeah.
mainly, so depending on the location and like that, they are utilizing conventional electrical energy.
And the second one is, now it is very curious to see that you have mentioned the DC bus is there, all the things are going there. As utility engineers now, our systems always in the national grid and the power utility side, we are maintaining AC system.
Yes.
How, if we go to a commercial level practice, how we combine these two? We are
Yes,
doing
of
all,
course. So,
yeah,
because I will explain it. Of course, our AC system is going to be there. We cannot replace that one. Okay. But let's say if we come from the application point of view, or when we want to integrate the electrolysis process on our power system network. Okay. So then, of course, we are going to take the electricity from the network, and for the electrolysis process, we need to have the DC system, right? DC power supply. So, of course, we need to have the power conversion units there. Okay, so then power conversion unit, then of course, then we are going to have this DC bus. Okay, so if it is a standalone, if it is a system which in which we have the objective only to produce the green hydrogen and use the grid electricity, then we don't need. But anyway, DC bus will be there. But on that DC bus, if you are integrating other renewables and again then fuel cell also and other things, then of course then we need to have this DC microgrid approach. Okay, maybe on a decentralized,
Right.
from the decentralized point of view.
That's right. And other thing, now,
Then on this decentralized point of view, when we have the DC bus, right? So then in future, when we will be having the electric vehicle charging stations also, so we know
yeah,
that DC bus is going to help us for fast charging also, right? So from the
yeah,
decentralized application point of view, right, that DC bus can also be used for electric vehicle fast charging stations also.
yes. Okay. Thank you so much. And other thing, now we know the Sri Lanka is very good wind country and offshore wind is there. Uh, we have another problem. Once we put offshore wind, the infrastructure facility like transmission network infrastructure facilities a little bit expensive and difficult. So
Yeah.
what would be the possibility? We are not connecting the grid and we are not connecting the transmission line. We just produce energy from the wind and converting it to the hydrogen. And do we have a good market to sell as
Yes, sir.
hydrogen?
That is a really good point, because that's what I was thinking also. Because when we have the offshore wind farm, right, and we don't want to get it connected to the main grid because due to the capital investment and like that, and maybe let's say we have the objective more on the green hydrogen production or hydrogen production. So by utilizing that intermittent energy from the at the offshore wind farm, right? So of course, then we have to convert it into the appropriate DC level, and then again we have to consider that whether we are using alkaline electrolysis process or which one. So then of course short-term energy storage will be there, and then we can produce that hydrogen offshore, and of course then we have to compress it and then we can fill it into the offshore storage tanks, and then we can ship it around the world also. So that is a good point also, and that technology is available in many countries also, because many countries they are doing the offshore oil and gas platforms are there, and they are producing the oil and gas offshore only, and then they are filling into the tanks in the ships, and then they are sending it to different countries, or where the applications are there, or where the requirement is there. So same approach can be used for the hydrogen also using offshore wind farm. Yeah.
Yes, thank you so much for your impressive speech and all the
So that's
questions.
why I believe that most of the Norwegian companies they are taking interest, because many oil and gas companies from the Norway they have very good expertise on offshore oil and gas platform, and taking that offshore gas and hydrocarbons basically and putting into that big ships tanks and like that, and sending it to all over around the world. So they may use the same technology which they have the expertise in transporting the hydrogen also.
Yes, thank you very much, Professor, and thank you very much, Dr.
Thank you.
Konar and Engineer Sara.
So I think all the questions have been answered. And yes, we'll share you with you all Professor Mohan's email address, so you can
Yes.
direct the questions to him as well. Over to you, Engineer Lakshani.
Yes. So thank you, Professor Kolte, for sharing your valuable insights with us. Your insights have provided us with a deeper understanding of green hydrogen energy and its potential in shaping a sustainable future. So now, to deliver the vote of thanks, I would like to invite Engineer Ms. Tirasara Gunaruwan, Secretary of the Electrical, Electronic and Telecommunication Engineering Sectional Committee, who is serving as an electrical engineer at RMA Consultants. Over to you.
Hello. So actually, it was a really interesting session. First of all, I would like to thank Professor Mohan for this interesting session. It was really a new topic for Sri Lankan engineers, so everyone was enthusiastic about learning on this topic. So I would like to really appreciate your speech here. And for organizing this, I would like to thank Dr. Konara and especially Engineer Zara, the chairman of the Electrical, Electronics and Telecommunication Engineering Sectional Committee. Thank you very much for your efforts in organizing this. And Engineer Lakshani, thank you very much for your support also here. And I would like to thank IESL Secretariat here for your support. So finally, thank you very much everyone who participated here. And I think we can conclude this session now.
Yes, thank you very much, everyone, and thank you for participating. Look forward to more sessions like this. Good night.